Teacher, what's the name of the presentation we're seeing?
Queries.
What's the name?
Oh, the name of presentation. Let me get out of here. And if you go to Brightspace, I'm going to go to the content section. There is a section class slides and other material, review basic statistical concepts. And it's this one here, AM003, review of descriptive statistics.
I only see up to the AM02.
Me too.
That's weird. Anybody can see the up to at the third presentation here in review of basic statistical concepts.
Yes, teacher, I can see it.
I can
You
see
can
it.
Yeah, me too.
You have to click on the review of basic statistical concept, then you can have all the list.
Ah, I found it. Thank you.
Okay. Okay, because if it shows here, unless it had something here, this thing of like hidden, then you wouldn't be able to see it, but it's available there. And if any of you have troubles, in any case, just let me know and I'll send you a mail with the presentation. No problem. Okay. So as you can see, the choice of age, which is the length of the interval, has an impact on how the histogram looks. A histogram like this looks very noisy. And a histogram like this looks much less noisy. This one is also, this is 0.3, but this 0.2 more noisy than this one. And there are ways to determine which is the best selection of age. Okay, but anyway, there's a dependency on the length of the interval, and there is a result.
I have a question.
2004. Yes.
How do I know how much interval to use, or like when?
Right here.
Oh, okay.
Hardel in other authors in 2004 show that an optimal value of age for n observations is given by this. Is 24 times the square root of n divided by n to the 1/3. Okay, so it's a result that usually works well for age. Most of the algorithms, when you don't specify either the number of intervals or the length of each of the interval, the algorithm will use this value. When you don't, most of the algorithms to build histograms use this value unless you specify a different value of age or number. There are some algorithms that work with the number of intervals and others with the length of the interval. Okay, but this is a good value of age. So I mentioned also that the value, the point where you start the histogram also has an impact on the shape. Here's the 4 examples of the same data set, the Swiss bank notes, where you start at different values of X naught. X naught is here we started at 137.65, 137.85, and so on. So there are some differences. However, the histogram, the shape of the histogram, the form of the histogram is more sensitive to age than to the starting point. But it depends on age, on the length of that interval. Okay. Now the kernel density estimates try to overcome some of the drawbacks that the histograms have. We saw that in a histogram we need to determine age. We need to choose where we start. We lose information because the observations that are placed, all of the observations in an interval are placed in the middle of that interval. Okay, so all of them are placed in the middle of that interval, and the density function of a continuous random variable is assumed to be smooth. However, the histogram is not smooth. It's just a bunch of rectangles, so it's not a smooth function. So those are the 4 drawbacks of histograms. And what the density estimates, kernel density estimates of PDFs do is try to overcome some of them. There will still be dependence on a smoothing type parameter. Okay. This is the first estimates, the first non-parametric estimates for densities were developed by Rosenblatt and Whittle and Parson in different years. And that's the first approach they did for a density estimation. So what they did is utilize a kernel function, which is a smooth function, okay? Because we know that for a continuous random variable, the density function is supposed to be smooth. So we replace a step function. If you look at this, and let me go back to the expression of the histogram. See how this is the estimate, okay? So the estimate is built based on indicator functions that are 1 if the observation falls in the given interval, okay, and will be 0 if it doesn't fall in that interval. So what they did is essentially, instead of counting this number of observations, which is this sum from I1 equals 1 to n, this is counting the number of observations that fall in a given interval, and that's what's wrong, right? Unless you can choose to have a relative frequency histogram, in which case this count is divided by the total number of observations. But this is essentially a step function. It takes the value 1 or 0. It takes 1 if the observation is in that particular interval, and it's 0 if it doesn't. Okay. That's it. That's the formula for the histogram. And what these guys did is they replaced, instead of having a histogram, which is this one here, which is the sum, the average 1 over n times h of the sum of these indicator functions. Its indicator functions are 1 if x minus x sub I for the ith observation is less than or equal to h over 2. So it's a step function that is 1 when the observation falls in that interval, and 0 if it doesn't. So if instead of if we write this equation here and write it, instead of writing this indicator function, we can think of this as a function k of u, which depends on the distance to the middle of a particular interval. And so you can write down the histogram, which is an estimate of the density function, as this average of kernels. This is a kernel function evaluated. We're evaluating this at x minus x sub I, because this function, it takes the absolute value of u. In this case, is the absolute value of x minus x sub I over h. And this is the general form of a kernel estimate. And the fact, and how can we depart from a discrete, just a bunch of boxes describing the distribution? What we can do is replace this function k by a continuous function. So, for example, we can use a quadratic kernel, which takes is defined as 15 over 16 I minus I 1 minus u. This is the u here, okay, squared times this indicator function. If we calculate x, not only in the center of the interval, but we can calculate it all over the interval. These are the most this is the most common kernel used to estimate a density function. We have the uniform kernel, which is this one here, the triangle, the Pagnikov quadratic, which is the one in the previous slide, and the most common kernel that is used is this one. This is the most common kernel to be used for a density estimation. Okay, so we definitely different kernels provide different estimators. However, there is not what it is very important in these kernel estimates is the smoothing parameter, is what's called the equivalent of the width, bandwidth, h, is the smoothing parameter. And this parameter can be chosen by cross-validation. We will talk about cross-validation later when we talk about resampling and in model fitting. But the concept of cross-validation is I evaluate the density estimate for different values of h and determine which is the one, which value of h gives me the best estimate in terms of the characteristics of that I expect from a density estimate. However, there is what you do is we minimize the squared error of the estimate minus the real density estimate, minus the real the PDF. Of course, we do not know the real PDF. So the way cross-validation works is essentially doing resampling to evaluate or to have an estimate of this square error, and that's how h is chosen. Okay, so we average the observations over a grid of points, and that's how we choose the grid. Let me erase this thing here. They show that asymptotically, if the grid size tends to 0, then we obtain the integrated mean square error if the grid size tends to 0. And what Silverman, this is I put the reference down here. Silverman used this fact here, and what he did was show that the using cross-validation, you select h, the value of h, that minimizes this squared deviation, integrated squared deviation. The most efficient form to calculate this thing. This is the result from Silverman. He found that a good value of h for the kernel density estimate using the Gaussian kernel, the normal kernel, is 1.06 sigma hat. That is the estimate of sigma from the sample times n to the minus 1/5. The way he did that is he takes the data, removes the first one observation, estimates the density for a given value of h. Then the same data takes the following information and estimates the density for different value for the same value of h. And then he repeats the whole process for removing one observation at a time to get an estimate of this square distance. And that's a normal, that's a density, a non-parametric density estimate based on a normal kernel. Okay. What happens if you know that your distribution, the data that you're working with comes from two different distributions, from a bimodal, for example, distribution, you can choose a bimodal kernel based either on the normal or based on the t distribution. Okay, so the fact that you use this kernel gives a lot of flexibility. This value for h is valid for a normal kernel, and using the normal kernel, and for n, any value of n. The value, this result works particularly well if n is greater than 20, 25 in the one-dimensional case, okay? But it's true for all n, but it works better for n greater than or equal to 20, 25. This is an example. We'll work with this later. But this is the Swiss bank notes. Swiss bank notes is a data set that we'll be using that has information on different measurements on there's bank notes that are legal, and there's some bank notes that are false, that have false bank notes. Now, they measure for the legal and for the false notes, you have measurements about the length, the height, distance from one border to the next, and so on. So these are taking one of those measurements and looking at the non-parametric density estimate of this particular measurement that was taken here. Here is the diagonal measurement. So if the bill, let me make a drawing here. These are the node. Let's see, this is the node. That's the node. And then do every bill, every node in the Swiss bank, as it happens in the Mexican bills that we use. Every bill has an inner corner, an inner frame. Okay, so I'm going to put it in different color here. I'm exaggerating here a little bit this thing, but anyway, there's several measurements that are taken on the bill. One of the measurements is how much does it measure on the diagonal. Another measurement is the distance between the top of the node and the inner frame, and the bottom of the node and the inner frame, and this is another distance that's measured. But here we're looking only at the diagonal. Okay, this is just looking at the diagonal. Okay, here's for how the diagonal of these nodes is distributed, and you can see the difference for the false, which are the red, and the genuine, the book banknotes. Okay, so it's more useful than the histogram because it gives us a smooth version of the density function, which is expected to be smooth for a continuous random variable. Okay, and let me take a break here. Okay, I'm gonna share my screen again. And let's now start with why multivariate analysis and so on. Let's see, key presentation. So far, what you have seen in your statistics classes has been the case where you're analyzing one variable. And you try to figure out its distribution. You want to make inferences about that distribution. You may want to estimate the mean and the variance, and then you try to build confidence intervals around for the true mean based on the sample data. You may also want to test hypotheses about the mean or the variance or whatever. In fact, in most cases, we have to deal with many variables. Okay, so we have n observations. If for each of these n observations, we have to analyze more than one variable. If you can think of, for example, a person who transacts in a bank, a customer of a bank, the same customer has several characteristics that may influence his behavior or her behavior in the bank. Whether the person is married or not, annual income, what else? Does he have children, or does she have children? when was the last race, and so on. So there's a bunch of data that we can relate to a particular subject, and in most of the real life situations. We will focus on observations that we obtain without controlling or manipulating other variables. There's one thing called statistical design of experiments. And statistical design of experiments, let me write it down here. Statistical design of experiments. In statistical design of experiments, we manipulate certain variables to see the effect that these changes in the variables have on a particular response that we're interested in. Okay, that happens a lot, for example, in medical research. Medical research, they design a lot of statistical experiments for different stages when you're developing a new drug, for example. You may want to study the effect of increasing or decreasing the dosage of a particular drug. You may want, in an industrial process, you may want to try to estimate the effect of changing the temperature and the viscosity in the process to see what happens with the hardness of the material that you are producing. So in many cases, you manipulate variables to observe a response. The cases we're working with here are not like that. See, what we're dealing with in this course is with observations that were obtained without controlling or manipulating other variables. Some of the key objectives that we have, whether it's scientific research or whether it's in applied applications, where the multivariate methods are the natural approach, are things like variable reduction. Variable reduction has to do with we have many variables, and we want to see if there's a smaller set of those variables that can represent the whole set, the variability that's inherent in the whole set. Classification. We may want to classify things based on their characteristics. For example, you have, in the case of a bank, you have customers who have default in their credit card payments. Okay, so you have customers who always pay on time, and they have certain variables or factors that characterize those customers, such as the demographic characteristics, but also their transactional behavior. So we may want to use that when we want to predict if a customer is going to default or not. So we classify customers in the good customers, the bad customers, let's say. Clustering is also something that we may want to use either in research or in applied applications. For example, most of you must have Netflix. Do you know how Netflix recommends a certain movie or certain program for you to watch? It's not only based on what you have seen in the past. What they do is clustering. What Netflix does is they do clustering. So they know what you've watched in the past, and they put you together with other people that behave in a similar way. And to all those people who behave in a similar way, they recommend the same type of movies or the same type of programs. So that's clustering is another useful thing that we are going to do. We're going to talk about clustering later in the course. We may want to study dependency among different variables. Okay, is one variable related to another variable? Is cancer related to smoking or not? Okay, we cannot say that smoking causes cancer. For that, we would need a controlled experiment, which in fact, in that particular case, couldn't be an ethical experiment. But from observational data, we can never infer cause and effect, but we can infer dependency, relationships. Okay, for prediction in many areas, in things, for example, sales prediction, or predicting whether a patient has a particular type of illness or not based on the clinical measurements that we have on that patient. We may also want to do hypothesis testing. The focus here in the class is going to be, we're going to cover variable reduction, we're going to cover classification, clustering, and prediction. Okay, we will not focus on inferences about associations, and we will not focus on hypothesis testing, but we will focus more on the other topics that I pointed out there. Okay. Now, what are the basic types of data analysis? One sample is with several characteristics or variables. The term characteristics, variables, or factors, or independent variables are used interchangeably. So when we talk about factors, we mean also independent variables or characteristics of a subject, of an observation. Okay. So we may be dealing with only one sample, and we may want to test hypotheses about the means of the different variables. Okay. We may want to find a small subset of the original variables, which explains most of the variability in the whole set, which is this is what's called the variable reduction methods. Express original variable dimensional reduction. So we want to reduce the dimension here. Express original variables as linear functions or other sets of functions, of other type of functions of other variables. If that's in the case, we have one sample with several characteristics or factors for each of the sampling unit. The sampling unit can be a person, a sampling unit can be a transaction, a sampling unit can be a bill, like the Swiss bank notes, one of those notes. So as each sampling unit is being measured for different characteristics. Okay, I'm sorry, I just saw the chat now. Okay, already somebody already answered. This is the AM01 introduction. Okay, AM01 introduction. Right, it's here, and then let me see, make sure he says it. Yeah, AM01 _1 introduction. Okay. So that's when we have one sample. Another situation can be that we have one sample with two sets of variables measured in each sampling unit. Okay. We may have two different sets of variables measured on each of the sampling units. And we may want to determine the number, magnitude, and nature of the relationships among both sets of variables. And that's what's called canonical correlation analysis. We will not cover this in this course. It was traditionally covered in the multivariate analysis course, but however, when we made the change to include the machine learning part, we had to remove some of the topics. But this is a type of analysis that's called canonical correlation. For example, we may want to relate a set of variables that measure interest with another set that measure achievement. Okay. Canonical correlation is something that, for example, psychologists and educators use a lot because they have two sets of variables in the same individual. For example, I may have a set of variables that measure family-related characteristics of the individual. Their parents are divorced, are not, the area where they live, do they have siblings, do they have let's say, do they practice sports and so on. And another set of variables may have to do with the academic performance. And the educators sometimes try to see if there's a relationship between those characteristics that that reflect the environment that the student is living with the student's performance. We may want to find a model to predict a set of variables based on the other. This is called multivariate multiple regression. For those of you who have taken regression analysis, you have one dependent variable and several independent variables, okay? In regression analysis, you have one dependent variable and several independent variables. When you want to predict one set of variables based on the other set, then you go into the area of multivariate multiple regression, okay? When you have the response is in fact a vector, okay? It has several, there are several responses that we glue together and try to relate those responses with a set of independent variables. That's multivariate multiple regression. The other case is when we have two or more samples which have several characteristics or factors or independent variables measured in each sampling unit. So we have two or more samples. One case is the multivariate analysis of variance, which is an extension of the analysis of variance that you probably studied in statistical methods. And here we use, remember in analysis of variance, in the univariate case, we use the t distribution and the f distribution to do some tests. The equivalent, the extension to the multivariate case of the t distribution is called the Hoteling's t-square distribution. And that's that the extension is called MANOVA, multivariate analysis of variance. Okay. We may want to find a combination of the variables that achieve a better separation between the two samples. Okay, so we have two samples or more. Okay, let's say let's talk about the case where we have two samples. We have two groups of people, and we want to be able to find a linear combination of the variables that we're measuring on each individual, so that we can get a better separation between the two samples. Okay. We may want to find a function of the variables that will allocate the units in the group that they belong to. Okay, that's essentially prediction. It's or classification. Okay, there's a very thin line between what's called prediction and what's called classification. The models are the same. The model that I use for classification is the model that I use for prediction. We may want to find the number of populations that gave rise to the sample data. We may not know which observations belong to which group. We know that we have different sets. For example, think of the potential customers of a bank. They do not have the information as to whether the particular potential customer is going to buy a credit card, is going to take a credit card from the bank or not. But they don't know how many different groups of people may be interested in a credit card, maybe or in which type of credit card. So if we have essentially a big population, but we know that there is more than one group in that population. So one problem would be to find how many groups do we actually have in this set of data, and that's clustering. That's a cluster analysis. Okay. So now let's talk about some general situations where multivariate methods are useful. One is in data reduction or simplification. What we pursue here is to construct a simple measurement of the response of cancer patients to radiotherapy based on measurements of several related variables. That's an example in medicine, okay? Another example would be measuring several characteristics of an individual's behavior to create a personality index. So we have many characteristics, and we summarize all those characteristics into one number, the personality index. That's dimension reduction, okay? Another objective could be classification and grouping. We can have several data from several variables associated with the use of computers. And based on that, they can create clusters of different types of computational tasks that allow the improving the respond to the needs of the users. Okay, so based on grouping the types of questions that people ask, for example, in a help desk, in an IT help desk, it helps you group the customers, the customers of the information technology area, and improve the service that you can give to them. This is another example where we have measurements on several psychological variables that were used to develop a procedure to discriminate alcoholics from non-alcoholics. Okay, so you measure several variables, and then you develop a model. In fact, what they do is develop a model to discriminate alcoholics from non-alcoholics. This is another example that is related to responses to certain visual stimuli were used to develop a rule to classify people suffering from a certain visual pathology. That's another case of classification, okay? And also prediction, because when I told you that there's a very thin line between classification and prediction, think of this particular case. You measure the responses of certain visual stimuli, and you develop a rule to classify people from suffering a certain visual pathology. If you have information on people who have developed that visual pathology, you can use this data to predict if a new individual is likely to suffer from that particular visual pathology. Another thing that, so we've talked about data reduction or simplification, classification, and grouping, investigation of the relationship among different variables. This is another example where data from several variables were used to identify factors that were key to the success of hiring external consultants. In prediction, there's many examples in prediction, associations among grades in several tests and variables that measure high performance in school. Okay, when to predict the success that the students will have in college, or measurements on certain accounting and financial indicators were used to develop a method to identify potentially insolvent insurance companies. So that's prediction. Before the insurance company becomes insolvent, then before that, we can predict that the insurance company is going to be in trouble. Okay, or before a student enters college, we may try to use this performance in his high school, or high school, or even previous studies like elementary school, to predict success in college. Okay, now statistical or machine learning. The course is called multivariate analysis and machine learning. The term most people use is machine learning. Particularly engineers use machine learning. Statisticians like myself tend to use the statistical learning more than machine learning, but we're a minority with respect to the number of engineers. So the term that prevails is the machine learning term. But statistical learning plays a very important role in different areas. Statistical learning is what we use for prediction. We use it for pattern recognition, for image recognition. Cognitive computing. Cognitive computing is when the computer understands natural language and responds in natural language. Okay, that's and what cognitive computing systems use. They use a lot of statistical methods or machine learning methods. Some of them very sophisticated. For example, they use something called deep learning. We'll talk about this what's artificial intelligence, what's statistical learning, what's deep learning. But that's an area where cognitive computing, machine learning, or statistical learning plays a very important role. When we put together statistical learning with optimization models, we can develop optimal marketing campaigns, for example. Not only the statistical learning will help me predict which customers will respond to a certain campaign. When we put together the prediction from a statistical model, a statistical prediction model, some predictive model, together with an optimization model, we optimize the cost of this campaign by minimizing the cost while we reach most of the people that will actually buy a particular product or a particular service. Rejection of an insurance application. So if we can assess the cost of rejecting an application, which is a good application, then we can not only develop a system that will recognize and recommend certain transactions to be rejected, it can also recommend whether the transaction, we can also suggest a real actionable thing saying reject that transaction, because we are playing with not only the prediction of the probability that the transaction will be fraudulent, but also with the cost of rejecting a transaction that is not fraudulent, okay, that is not fraud. Rejection of a claim, changes in product schedules. Again, statistical learning with optimization models play important role in determining actions to be followed to minimize costs and optimize whatever we're trying to achieve. Get more customers to buy my product, or get or approve applications that are really good applications, legal applications. Okay, this is the term artificial intelligence. The term has been used since 1940 something, 1942, 1943, where computing power was very, very, very scarce. There was nothing like what we have now in the 1940s. In the 1940s, the computers were huge things that were very limited in memory and in processing types of the type of processing that they could do. But the term artificial intelligence stands for any technique that enables the computers to imitate human intelligence. Okay, any technique. So when these things started in the 1940s, in fact, the sort of things that the computer did were very basic rule-based actions. Okay, for example, you could program a computer to say, if the ticket, if the sale is more than $10, then apply a 1% discount. If the sale is greater than $100, then apply a 2% discount. Exactly. So those are deterministic rules that were programmed in those computers in the 1940s. But artificial intelligence also includes what we use now, which is more complicated models which fall now into the realm of what's called machine or statistical learning. And the artificial intelligence includes also deep learning. Okay. Just to give you an idea of how computational power has evolved, the first job I had was in an insurance, in a company that no longer exists in Mexico, which is, it was called Celanese Mexicana. I started working when I was in the second semester. I studied actuarial sciences in the UNAM, in the National University, in la Facultad de Ciencias. And I started working the second semester. And I was working as a programmer. we had an IBM 360, and we were migrating. They hired me because they were migrating to an IBM 370 132. It was 370 132. That computer occupied, let's say, around probably 40 square meters, the whole computer. It had to be air conditioned. And the memory that that computer had was 132K. 132K. What you have in any of your smartphones, it's much more than that. Okay, and that was 132K. That was the capability that we had. So what the sort of process we had, for example, we had the payroll was automated. So, but that was a very simple process, because you take in a database, there's the salaries, and then you make the process so that the employees are paid. And there were very simple processes, because all you could do with this computing power was very simple rules. Machine learning or statistical learning is a part of artificial intelligence that includes very complex statistical models to enable computers to improve certain tasks without experience. Okay, and it includes deep learning. Okay, deep learning is part of this thing. So the algorithms we're going to study here are part of this, are part of machine learning or statistical learning. These are more sophisticated methods that many years ago could not be computed. In fact, when you took the class statistical mathematics, and when you took probability and statistical mathematics or whatever, in statistical mathematics, you see a lot of theorems and axioms and all that. Well, those theorems are still true, and the theory hasn't changed that much. What has changed is the capability that we have now to apply the theory. Before, there were many things that were developed in theory that we were not able to do them in practice because of the computational power limitations. If you review some of the statistical textbooks from many years ago, they place a lot of emphasis on how do you compute this thing. For example, look at an old linear algebra book, and they will place a lot of emphasis on how you manually can invert a matrix, because it was very difficult to do matrix inversion for large matrices. It would take forever in a computer in the 70s or in the 80s. Okay, so a lot of the methods have now evolved because of the capabilities that we have in computers. And deep learning is the part of machine learning that is based on algorithms that enable software to train itself to execute complex tasks, such as natural language processing. NLP is natural language processing. Image recognition, recurrent and convolutional neural networks are the key in this deep learning. So I will try to see if we can cover at least the basic neural networks, so you know what the basic neural networks do and how they work. And these are much more complex neural networks that are required for this type of deep learning, what's called deep learning. So, but we'll be learning things in this area here without entering the domain of deep learning. Now, statistical learning is divided in supervised and unsupervised learning. Okay, so what I say here is statistical learning is based on several tools and methodologies to understand and extract actionable information from data. We have a lot of data in the world, a lot of data that sits around of course in a particular company in their systems, but there's also a lot of data that floats around the internet. Okay, everybody has Twitter, and Facebook, and that's data that can be now used to make predictions. Okay, well, I can predict if a customer that is somebody who's trying to buy a health insurance policy from an insurance company. We can predict based on what we know about this customer and the things that he tweets and stuff like that, and we can probably predict if the customer is gonna be a good customer or is gonna try to make a fraud to our company. So the statistical learning is divided in unsupervised and supervised learning. Unsupervised learning, there are two key objectives here, and the one I put here is to group elements into that have not been labeled in clusters. That's one of the key objectives. Another, within this area of unsupervised learning also falls the area of the dimension reduction. Okay, if we want to reduce the number of variables, it's also unsupervised learning. I should add that here. But the main objective that we're going to focus in this class is to group elements that have not been labeled according to some measure of similarity. So we'll see if, for example, a bank has a bunch of customers, and they don't know if a particular product that they're trying to develop is going to be successful with all of them. So what's the first thing they do? They try to group their customers into similar groups, and that's called clustering. That's cluster analysis. I don't know if the different groups will be if one group is going to buy a product or not. I don't know that. Okay, but I can group them in according to their similarity, and in such a way that customers within a cluster are as similar as possible, and customers in different clusters are very different. So that's unsupervised because I don't have a label for the customers. I don't know if I have 3 groups of customers or 4 or 5. What I know is that there's more than one group in my customers. And then that's one of the objectives. The other one is to reduce dimensionality. I added that. I forgot I didn't put it. Supervised learning is our main objective in supervised learning is to learn. I'm using the word learn here intentionally instead of the word fit. It's the same. We're trying to fit a function that relates a series of known inputs, factors, independent variables, predictors, with a known response or target variable. So, for example, I have think of people who have a certain type of cancer and people who don't. I know the clinical characteristics of the people who have a certain type of cancer, and I know the same characteristics of the people who don't. Okay. For example, think of lung cancer. Well, have a bunch of people that I know their age, I know how much they weigh, I know if they smoke or not, I know if they are married or not, I know where they live, and I have a group that has gotten this type of cancer, lung cancer, and another group with the same measurements that do not have cancer. They've developed maybe a tumor, but it was not cancer. Okay, so based on that set of observations of people, I want to learn a function that will help me predict for a new patient whether or not that patient is very likely to have cancer or not. Okay, so the objective is to learn a function that relates a series of inputs with a known response. That's why it's called supervised, because I know I know, for example, in this example I was giving you, I know that I have two groups of people. I know that I have a group of people who develop lung cancer and a group of people who don't develop lung cancer. In a bank, I know in the history of my bank, the last 2 years, the last 3 years, I know which of my customers have always paid their credit card, and I know which of those customers have not paid on time. And some of them I even had to send them to a collection agency. So I have the information on the customer and I have a response. Okay. And we can use this function for classification or prediction purposes, either to classify the good ones and the bad ones, but also to predict. When a new customer comes, I can try to use the characteristics of that new customer to predict if the customer is going to be a good or a bad customer. Okay. Now, talking about supervised learning, there it's 45 minutes. I'm trying to go no more than 45 minutes. So we'll talk about this thing at 12. We'll take a break again. Okay. There are two types of supervised learning. One is regression, and for those of you who have taken regression analysis, regression is when your response or target variable is continuous. Okay. For example, you want to be able to relate height with weight. And you have a model where in regression, you have your response is y equal, let's see, beta null plus beta 1 x plus epsilon. That's the simple linear regression case, right? I only have one variable. My response here, y is height and x is weight. This is height. So I may want to try to relate height with weight through this linear model. That's a regression because my response is continuous. It's not limited to one variable. I can have more than one variable. I can have x1 plus beta 2, x2, and maybe this is weight, and maybe this is let me see, age. Okay, plus random error. So that's a case. That's supervised learning, because for a bunch of individuals, I already have their height, and I have their weight, and I have their age. So when another individual comes and I ask him, and I look at his weight or her weight and his or her age, then I can try to predict their height based on those two variables. Okay, so that when the response is continuous, it's called regression. We will not focus on this part because you do that in the regression analysis course. We will focus on classification. That's when the response or target variable is categorical. Could be 2 categories or for 3, 4 categories, whatever. The input variables in both cases, in regression and classification, can be numerical or it can be continuous or not. Okay. For example, I can also a variable here. I can have plus beta 3 and gender. X3 may be gender, whether it's a male or female. Okay, because that relationship may depend on whether the individual is male or female. So we have more than we can have many variables. They can be these variables are called the predictors, or the factors that I'm measuring to predict this height. And they can be either continuous, they can be discrete, they can be categorical, whatever. And the same thing happens in classification. In classification, my target is categorical. So my target would be of the type, the type, for example, 1 is cancer, 0 is not. Or it could be of the type, my response could be 1 if is, let's say, if it's schizophrenic. It could be 0 if it's if there's doubt, okay, not certain, and could be -1 if it's if not schizophrenic. Okay. So I have many categories here. We will focus because of ease of notation. Just to keep the notation simple, we will focus more on the case where you have a binary response, whether it's cancer or not, it's fraud or not, is money laundry or not. Okay. So that's a supervised learning, and we'll be focusing on the categorical response, on classification. Classification, which is also prediction. I should say here classification and prediction, but then I should also have to say here is regression or prediction, okay? Because we can use a regression equation to predict. We can use a classification model to predict also the response, the category for a new subject, okay? So let's take a small break here. Let me see here, post recording.